Welcome to today's tutorial. Today's tutorial is going to be about vector span. So first let me write down the definition of span. Spanning a vector or two vectors AB and CD would be equal to lambda 1 times AB plus lambda 2 times CD, and here we have the lambda 1 and lambda 2 are elements of the real number set, so they could be any real number. Now let's show this graphically. So if you have your axes here, let's say the vector AB looks something like this. So this is your vector AB. Now, if you want to extend the vector AB here, this will be on the same line, so we could just extend it here. And then maybe up till here, the extension would be 2 times AB. And maybe up till here it is 3 times AB. So in general, you could say any extension on AB would be lambda 1 times, so any real number, times AB. It could also be on the opposite direction. So here you could have this way, you could have here minus 3 times AB. Now let's draw vector CD. So let's say vector CD is something that looks like this. So any extension on this here is known as lambda 2 times CD. So you can multiply any real numbers, lambda 1 and lambda 2, and that would be in the span of these two vectors. Now, if you draw a parallelogram out of this, a parallelogram, let's say from the end of vector AB, we will draw a line parallel to CD. So here, let's draw a line parallel to CD. And from the end of CD, we'll draw a line parallel to AB. So this vector here now that we got, this position here, is the lambda 1 times AB plus lambda 2 times CD. Okay? So here you can say that maybe if we just say lambda 1 times AB plus lambda 2 times CD is any vector xy, then you can say that xy is the diagonal of the parallelogram spanned by the vectors lambda 1 times AB plus lambda 2 times CD. So you can say here maybe x, y is the diagonal of the parallelogram spanned by vectors lambda 1 times AB and lambda 2 times CD. Okay, so let's consider two n is equal to 2-dimensional vectors v1 and where we have the elements 1 and minus 1, and v2, vector v2, which is having the elements minus 3 and 1. So we know from the previous work what we just did, we have lambda 1 times the vector 1, which is 1 minus 1 plus lambda 2 times the vector minus 3 minus 1 is equal to the general vector. Let's say it now, previously I wrote xy, but now I would call it AB. Okay, so here now, to find out what we can do here, we can find out lambda 1 and lambda 2. So to do that, what we first do is we'll write it as a system of linear equations. So this would be now written as 1 times lambda 1, so that's lambda 1 plus minus 3 times lambda 2, that's minus 3 lambda 2, and then we have here minus lambda 1 minus lambda 2, which is equal to AB. Okay, so writing this here, it would give us lambda 1 minus 3 lambda 2 is equal to A, and minus lambda 1 minus lambda 2 is equal to B. Now, considering our second equation here, we would get here, so this would be, you can say, okay, I'll write it again here. So we have minus lambda 1 minus lambda 2 is equal to B, and that would be same as saying that minus lambda 2 minus lambda 1 is equal to B plus lambda 2. Thus we can say that lambda 1 is equal to minus B minus lambda 2. Okay, now let's take our first equation. We have here lambda 1 minus 3 lambda 2 is equal to A. Now replacing our lambda 1 value inside the second equation, here we'll get minus B minus lambda 2 minus 3 lambda 2 is equal to A. So here we have minus B minus 4 lambda 2 is equal to A, and then we can write this in terms of lambda 2, which would be A plus B divided by minus 4, that can be written as minus a minus b divided by 4. So that's lambda 2 for us. We just got the general values for lambda 1 and lambda 2. But still we got lambda 1 here in terms of lambda 2, so we will work it out further to get it only in terms of a and b. So you can say since lambda 1 is equal to minus b minus lambda 2 and lambda 2 is equal to minus a minus b divided by 4, we have lambda 1 equal to minus b. So instead of lambda 2, we'll replace it now here with minus a minus b divided by 4, and that will be equal to minus b plus a plus b divided by 4. Okay, here this part is divided by 4, so to make the denominator same, to be making it divided by 4, here we have to multiply down by 4 and even above by 4 here. So that would be minus 4b plus a plus b divided by 4, and that is equal to minus 3b plus a divided by 4, which can be written as a minus 3b divided by 4. Okay, so we got the final value for lambda 1, 2 now. So you can say that lambda 1 is equal to a minus 3b divided by 4, and lambda 2 is equal to minus a minus b divided by 4. So now they are in terms of only a and b. Now we have to check whether the lambda 1 and lambda 2 indeed satisfy the equation here. So the equation that we wrote at the beginning, that was lambda 1 times 1 minus 1 plus lambda 2 times minus 3 minus 1 is equal to a b. So let's put the values of lambda 1 and lambda 2 in this and check whether do we actually get a and b or not. I'll copy this equation and let's work it out here now. So we'll replace here lambda 1 with a minus 3b divided by 4 times 1 minus 1 plus we have minus a minus b divided by 4 times minus 3 minus 1. So that gives us here, we have a minus 3b divided by 4 times 1, which is the same value, minus 3 times minus a minus b divided by 4. And then we have here minus 1 times a minus 3b divided by 4 minus 1 times minus a minus b divided by 4. So now that if you solve a step further, we now get here a minus 3b divided by 4 plus 3a plus 3b divided by 4, and here we'll get minus a plus 3b divided by 4 plus we have a plus b divided by 4. Now that if you add it up, you have here denominator same, so you just can add up the numerators. A minus 3b plus 3a plus 3b divided by 4, and here down you have minus a plus 3b plus a plus b divided by 4. So minus 3a, sorry, that doesn't cancel. It's minus 3b and plus 3b cancels here, and here we have minus a and plus a that cancels. So now simplified, the values will be a plus 3a, which we can write it as 4a divided by 4, and down we have 3b plus b, which is 4b divided by 4. So 4 and 4 will cancel, and that will be equal to a and b. So that's checked, that when you put in the lambda values that we just got, we get a and b as general again. So now we can say that AB is any diagonal that is spanned by the vectors lambda 1 times 1 minus 1 and lambda 2 times minus 3 and minus 1. So AB could be any number, any vector on the plane. Let's choose the vector. Let's choose any vector that we want. So maybe let's choose here. For AB, let's choose the vector 11, 1. So that will be equal to lambda 1 times V1 plus lambda 2 times V2. So here we have now replacing the lambda 1. So here we'll replace it with the values of lambda 1 as a minus 3b divided by 4. So here you have a minus 3b divided by 4 times the vector 1, which is 1 and minus 1, plus we have for lambda 2 minus a minus b divided by 4. So we have minus a minus b divided by 4 times vector 2, that is minus 3 and minus 1. So these values here are our a and b. So we can replace that here. Now we have 11 minus 3 times 1, that's 3, divided by 4, which is 8 divided by 4, that's 2. So I can just write it as 2 here now, times 1 minus 1, plus we have minus a minus b. So minus a is 11, minus b is 1, that's minus 12 divided by 4, and that would be minus 3, times we have here minus 3 minus 1, and this if you solve it, here you will get 2 times 1, that's 2 minus times minus is plus, so we have plus 3 times 3 is 9, and then here we have 2 times minus 1 is minus 2, and plus we have 3 minus 3 times minus 1 is 3, so that is equal to 2 plus 9 is 11, and 3 minus 2 is 1. So you can see that we can take any number or any vector AB, and we can get our real numbers lambda 1 and lambda 2 as we got here. So you can say that once you have the two vectors here, that's lambda 1 times 1 minus 1 and lambda 2 times minus 3 minus 1. Any vector in the plane is spanned by these two vectors, any vector in the plane, but not necessarily the values that we got here. It could be any real values, lambda 1 and lambda 2. So now we can draw this here down and see whether our parallelogram is right. So maybe I'll draw it on a different page. So here we have our vectors 1 and minus 1. So here we have 0, 1, 2, 3, 4. So I'm just roughly drawing the graph here. So we have 1 and minus 1, that would be this point here. And then we have minus 3 minus 1, so that's minus 3 and minus 1. Which, let me take a different color for that. And now what we need to do is we need to find out, or we need to draw the parallelogram for our point here. Okay, so now we have got our diagonal is 11, 1. So here we have or maybe let's not draw the diagonal at first, but we can multiply our lambda values. So here we have 2 times 1 minus 1, that is, we have 2 minus 2. So we have to draw this vector on the same line here of the vector 1, 1. So that's 2 minus 2, which is here. That's an extension. Okay, that's your 2 minus 2. And then we have the extension for the other vector. Stepping for that. So here we have 9 and 3. So that's the vector 9, 3. Extension of 3 minus 3 minus 1. We need for 9 one more value here, and then we have here 3. Okay. So that's an extension for the green graph, but I'm just drawing it in pink. Alright, so here we have now our new values. So this one here is, or we can just write this -3 times -3 minus 1, and this one here is 2 times 1 minus 1. Okay, now we'll have to draw the parallelogram. So we'll go to this point here and draw a parallel line to 2 times 1 minus 1. So that would be the parallel line. And then we'll draw from the vector 2 times 1 minus 1, the parallel line to 3 times -3 minus 1. Okay, so this point here is 11, 1. So as you can see over here, we have 9, and up to here we have 10, and this is, okay, my bad. It's not very accurate. So we have here 9, 10, that's 11, and here we have 1. Okay, so that's the diagonal. Of the parallelogram from the origin, which is 0, 0. So you can say here 11, 1 is the diagonal of the parallelogram that is spanned by the vectors 2 times 1 minus 1 and -3 times -3 minus 1. And that's the end.